Oh, enter your attendance now. Enter your attendance in the chat box now. Type your roll number in the chat box. The first roll number I can see here in the chat box is that 2101 BS364. If anyone entered your attendance before 2101 BS364, you can enter your attendance again. 364 is the first roll number I see in my chat box. Okay, let's start. So in our last lecture, we have introduced one of the spherical coordinate system, which is a cylindrical coordinate system. Here we talk about the coordinate variables of this spherical coordinate system. So here in the coordinate, one of the coordinate variable that is corresponding to u1 is rho. Another coordinate variable is your phi, and another one is your z. So you have three coordinate variables, and we discuss about the coordinate lines, that this is straight line, this is a curve, or in fact a circle, this is also a straight line. And also we discuss about the coordinate surfaces here, right? And also we talk about this transformation relations. Here the transformation relations here is that x can be expressed as a function of rho phi z coordinate system. X can be written as rho cos phi, y can be written as rho sin phi, z is z. And this is the reverse transformation. Rho can be written as like this, phi can be expressed like this, z can be expressed like this. So rho, one of the coordinate variable of cylindrical coordinate system, can be expressed as a square root of x square y square, that is function of x, y, which is the Cartesian coordinate variables, right? So these are the things we talk about. Now, what are the scale factors now? Here, as I said, in this cylindrical coordinate system, u1 is rho, u2 is phi, u3 is z. Rho, phi, z coordinate system is your cylindrical system. Now, h1, the scale factor corresponding to u1, you have to denote it as h rho. The scale factor corresponding to u2, just mute.
The day I go offline and start studying seriously, it's over for you.
So the scale factor h2, which corresponds to the coordinate variable u2, like we discussed before, what was that? H2 was, it was del position vector derived differentiation with u2 magnitude. This was your h2, you remember that. So u2 is now your phi coordinate variable. So h2 will be denoted as h phi. H3 is denoted as hz. And what will be the position vector in this cylindrical system? You know that the position vector in Cartesian system, this is your 3D Cartesian system. Cartesian system can be expressed like xi cap yj cap plus zk cap. So if you're going to write in terms of cylindrical system, x from this transformation relation, x is rho cos phi, y is rho sin phi, z is z. So you have to put x as rho cos phi, y as rho sin phi, and this will be your position vector. Now, how do you get your tangential unit vectors? In order to get tangential unit vectors, what you have to do is you have to differentiate the position vector, tangential unit vector along rho, which we call it rho cap, will be differentiation of your position vector with respect to the coordinate variable rho. So earlier you remember that in order to obtain what is that E1 cap, what we did was differentiate position vector with U1 and then dividing with the magnitude like this. So this is how we get the unit vectors in general orthogonal curvilinear coordinate system. But in this specific cylindrical coordinate system, your position vector, in place of u1 you now have rho, so del r divided by del rho divided by magnitude of that unit, that vector. This will give me your tangential unit vectors, and this term is called your scale factor, your h rho here. The scale factor h rho is del r upon del rho magnitude. So if you differentiate this r with respect to rho here, differentiate the first term, differentiation of rho with respect to rho is 1. The remaining will be cos phi I cap. Second term, if we differentiate, this rho has to be differentiated with rho, that will be 1, and then the remaining is sin phi j cap. Now, if we differentiate the third term, differentiation of z with respect to rho will be 0 in cylindrical coordinate system. For your cylindrical coordinate system, del z upon del rho is 0. Why is that? Because you know z is a coordinate variable, rho is a coordinate variable, coordinate lines, another coordinate lines. So these coordinate variables are independent to each other. Z is independent of phi, z is independent of rho, and similarly, rho is independent of the other two variables. Just like the coordinate variables in 3D Cartesian system, x, y, z, differentiation of z with respect to x is 0, differentiation of z with respect to y is 0. Why is that? Because these coordinate variables along z or variables along y and x, they are all independent. Similar to that, the coordinate variables rho, phi, and z, they are independent. So del z upon del rho is 0. Therefore, if you take the magnitude of this, you know how to take the magnitude of a vector quantity. You have to take the square root, and then you have to take the coefficient, square root or square of this coefficient, square of this j cap coefficient, that is cos square plus sin square, that will be 1. And the scale factor along phi coordinate, along the u2 or phi coordinate will be denoted as h phi. So this will be del r upon del phi, and take the magnitude of that. So if you differentiate this del r with respect to phi, rho is constant with respect to phi. Here what you can differentiate is cos phi. Differentiation of cos phi is minus sin phi. So here you see that rho minus sin phi. And similarly, differentiation of sine is cosine. So rho still remains there, rho cosine phi. So if you take a magnitude of that, mod of that, then rho square will be, you can rho square sine square phi here, rho square cos square phi here. Rho square can be taken as a common, and then you can take it out as a square root. So if you take it out as from the square root, it will be rho. So sine square plus cosine square is 1 again. So this is what you get. The scale factor h phi is this. Now the scale factor is z. Differentiate this r vector with respect to z. Differentiation of the first term with respect to z will be 0, because rho is independent of z. Phi is independent of z as an independent coordinate variable. So this term you differentiate, it is 0. And similarly, this term you differentiate with respect to z, it will be 0. Differentiation of z with respect to z is 1. So what remains here is k cap. Magnitude of k cap unit vector is 1 itself. Okay. So this we have discussed the coordinate surface and the coordinate lines. Now In order to get the unit vectors, simply you have to do that differentiation of this tangential vector del r upon del rho divided by the scale factor of the magnitude. So if you remember how we discuss how we get the scale factor, this is what you're going to get. This is 1. This is what you will get, right? So, and similarly here, if you follow this, the way we are writing, what is that? E2 cap del r upon del u2 divided by magnitude of del r upon del u2. This was our tangential unit vectors. In place of u2, we now have ur phi coordinate variable. So this, if you perform this mathematical differentiation and division and all, this is what you're going to get. And similarly here, this is what you're going to get. So these are the 3 unit vectors in this cylindrical coordinate system. The 3 unit vectors in this cylindrical coordinate system. These 3 unit vectors, you have to kind of remember it. You can work it out, you can easily obtain it, but you can kind of remember it also. So this was something I've written earlier. Now, this is one example that we can quickly go to. Here, differentiation of unit vector, tangential unit vector along the rho coordinate, that is E rho cap, is equal to phi dot. Here there is a dot here. You remember, if you look at this closely, this is a phi dot. Whenever you put a dot on top of it, it means that this is differentiation of phi with respect to time. Okay, so let's see. So you differentiate this E rho with respect to the time. So E rho is this quantity. Differentiation of cosine phi is minus sine phi. Phi, if it is a variable with respect to time, then again you have to differentiate phi with respect to time, d phi upon dt. I hope you are aware of this thing. See, if you have a function of this thing, functions, if you have a function of functions, something like this, if you differentiate this function with respect to x, differentiate this first, differentiation of this first, and then differentiate the function again. Okay, that's how we do it, differentiation of function. So if phi is a function of time, cosine phi is a function of phi. So differentiation of cosine phi is minus sine phi. Phi differentiate with respect to time again. This is what you will get if you differentiate here. So if you take this as a common factor, and this is what will remain here. If you remember, this is your E rho. This is your, sorry, E phi, unit vector corresponding to phi coordinate variable. And if you denote this d phi upon dt as phi dot, this is what you're going to get. So this is quite simple. And similarly, you can do the time derivative of your unit vector along the tangential unit vector along the phi coordinate E phi. So E phi is this quantity. Just perform a time derivative. Differentiation of sine phi is cosine phi, and you have to differentiate phi again with respect to time, because phi is a function of time, sine phi is a function of phi. So differentiation of function. And so if you follow this simple differentiation minus, this is what you're going to get. So I think there's no need to spend so much time here. d phi upon dt, you denote it as a phi dot. So this dot has to be there to represent the time derivative. So these are some very simple things. And also you can prove that cylindrical coordinate system is orthogonal. Cylindrical coordinate system, as we discussed, the coordinate surface like rho equal to C1, phi equal to C2, and z equal to C3. When we discussed this coordinate surface, we found that rho equal to C1 was a curved surface, right? So we already see that now cylindrical coordinate system is a curvilinear coordinate system, because one of the coordinate surface is curved. That is a curvilinear coordinate system, right? So now again, you can show that this curvilinear coordinate system, cylindrical coordinate system, is in fact orthogonal curvilinear coordinate system, right? So in order to do that, we have to see that the dot product between the unit vectors are 0. Dot product between unit vectors are 0. So you just perform a dot product this thing, you will find that I dot I is 1, I dot j is 0, so you will get minus of cosine phi sine phi, and similarly this, and it will be 0. If you perform the dot product of this will be 0. If you perform the product of this, you will find that it is 0. That means all the tangential unit vectors in the cylindrical coordinate systems are mutually perpendicular, and therefore it is an orthogonal system. And this is again one simple example. You can express grad phi, divergence of a vector, curl of a vector field in cylindrical coordinate system. In cylindrical coordinate system, u1 is rho, u2 is phi, u3 is z, and these are the scale factors. H1 is h rho. This should be rho, not p. Okay, h1 is h rho, that is 1. We have seen that. H rho, h2 is h phi, that is rho. H3 is hz, that is 1, which we have seen that. And you know that this uh, gradient or the del operator was, what was that, 1 upon h 1 del upon del u1 e1 plus 1 upon h2 del upon del u2 e2 cap plus 1 upon h3 del upon del u3 e3 cap. So this was your del operator when for the general orthogonal curvilinear coordinate system. You just put h1 as h rho, which is in fact 1. So just substitute the scale factors. H2 as h phi, that is rho. H3 as hz, that is 1. So u1 as rho, u2 as phi, u3 as z. So this is what you're going to get as a gradient. And this was the expression we derived for the divergence of a vector field for general orthogonal curvilinear coordinate system. You just substitute the value of h1, h2, h3 here. H1 is 1, h2 is rho, h3 is 1. So this is what you will get. And similarly, u1, u2, u3, you substitute. This is your divergence. So Carl also, this was your expression for Carl. So you remember, I think you can browse back also your notes. The Carl general curvilinear coordinates Carl expression, it is there. So you just substitute h1, h2, h3, and u1, u2, u3. This is what you're going to get. Okay. Now, this vector also you can express in cylindrical coordinates. This is a vector. This is a vector field in Cartesian system. This is a vector field in 3D Cartesian system. You can convert in cylindrical coordinate system. Z, you know, Z is corresponding to Z from the transformation relation. X is rho cos phi, Y is rho sine phi, and we know that E rho is this, E phi is this, Ez is this, and if you multiply E rho with cosine phi, this is what you're going to get. If you multiply E phi with sine phi, if you look at this, E rho and E phi, this is what you're going to get. If you subtract these two, you will eliminate J here. If you subtract these two, this and this will cancel out, and you will get this term, that is I cap. So I cap can be written as this. And similarly, if you multiply with this and multiply with this and then do the addition, then you can express J cap in terms of E rho and E phi. And then in the cylindrical coordinate system, you can put I as J as this, J as this, and J as this, and I as this. Okay, so if you put all these things in this particular expression after putting Z as Z, X as rho cos phi, Y as rho sine phi, and actually your K cap is equal to Ez cap. Okay, so I and J, if you do that and you rearrange it, then this is what you're going to get. So this is the vector field in cylindrical coordinate systems. The unit vectors are E rho, E phi, and Ez here. So it's quite simple, and I will discuss this spherical coordinate system. Unfortunately, I will not be able to take class tonight because this week I'm completely engaged with other works. So this will be our last class for this week. And whatever topics we have covered so far, please go through it. That will be for your CAT 1. And I think I will finish the syllabus in five, 6 lectures after CAT 2. So this again is another spherical coordinate system, sorry, curvilinear coordinate system. Why do we call this a curvilinear coordinate system? If you look at this, in the spherical coordinate system, instead of using, instead of using u1, u2, u3, we are going to use r, phi, and z coordinate system. R, phi, and z coordinate system. So, in our 3D Cartesian system, 3D Cartesian system is x, y, z coordinate system. We can define the location of any point here in 3D Cartesian system. Once we know what is that, if you drop a perpendicular here, if you drop a perpendicular on the z axis, then this is your z coordinate variable value. If you draw a perpendicular on the xy plane, and from this point, if you draw a perpendicular on the y here, this is going to be your y coordinate value. This is, if you draw a perpendicular, this is going to be your x coordinate value. Once this x, y, and z coordinate values are known, then you can identify the point, like I said before, in the 3D Cartesian system. This is your 3D Cartesian system, right? So another method of another coordinate system approach, another coordinate system here is your spherical system, in which we define the location of this point by identifying the distance from the origin, which we call it r, the distance from the origin. This is your one coordinate variable, r, the distance from the origin. And if you draw a perpendicular here, and from here, if you measure this distance, if you draw a line here and measure the angle here, this angle we call it phi. So if this angle subtended with respect to x is known, and also if the angle subtended with respect to theta, sorry, the angle subtended with respect to z, which we call it theta. The angle subtended with respect to z is theta. So if this angle and if this angle is also known, then the location of this point can be identified using your rho, phi, and theta coordinate system. Rho, phi, and theta coordinate system. So this angle has to be known, this angle has to be known. Now, what are the limits of this coordinate variable? You know, r can go from, r is a measure of the distance from the origin. R can go from 0 to infinity. This is the limit you can choose. And in order to cover the, in order to identify any point in this three-dimensional coordinate system, three-dimensional space, you have to extend up to infinity, right? Now, again, phi coordinate also, in order to identify any point in the front side of your screen and also on the back side of your screen. In order to identify any point in the front side of the screen that is towards you, and also to identify any point on the back side of the screen, phi has to extend from 0 to 2 pi. Okay, phi has to rotate around 0 to 2 pi. Now, so you see that by phi rotation from 0 to 2 pi, we can cover any space from the front side to the back side, and it's right. Now, this theta, what will be the limit of this theta? Theta, if you to cover any point above, to cover any point above xy plane and below xy plane, above and below xy plane, in order to cover that, your theta has to go from 0 to pi. Okay, so if you go start from theta 0, it starts from here, and if you increase your theta, you will go over, and if you come to this angle, this is your pi angle. So if you rotate theta from 0 to pi, this will cover the whole space above and below. But you don't need to rotate around 2 pi. This is not needed. Why is that? Because if you want to arrive at any point here on the back side, if you want to arrive at any point here on the back side, it is sufficient to rotate your phi here. It is sufficient to rotate your phi around this thing. So phi is already rotated around, that is 0 to 2 pi. So yeah, theta, you don't need to rotate up to 2 pi. Once you rotate up to pi, then you can rotate your phi around it. So once you rotate your phi like this, you can go to any point on this thing above the xy plane, below the xy plane, on the left side also you can go once you rotate your phi from 0 to 2 pi. So the limits for these things are identified. Just a minute. 그러면은 그거는 어떤 것도 그러면 한번 더 그럼 그저 자이 또야 매 누나 하고 그러다 이게 저를 저다 소물 또한번 더 나와 So I hope you understand, like in order to cover any point in this three-dimensional space, these are the limits of these coordinate variables we have to choose. Like, in the x, y, z coordinate system, in order to cover any point, you have to choose x variable from minus infinity to plus infinity. Why is that? Because you need to go up to to identify any point on the back side here, you have to extend x to minus infinity, and to identify any point on the front side here, you have to extend x from to plus infinity. And similarly, in order to identify any point on the left side, you have to extend y variable from minus infinity to plus infinity. And similarly, to identify any point above and below the xy plane, z has to vary from minus infinity to plus infinity. So that's how we have to do it in this 3D Cartesian system to cover any point in the space or to identify any point in the space. Similar to that, in this spherical coordinate system, like the ones on here, rho r phi is theta. To identify any point, you have to go from 0 to infinity. So you might wonder, some of you might wonder, why we are not going r from minus infinity. There is no minus infinity here in r coordinate variable here. R is simply a measure of the distance from the origin. So if you arrive at the origin, R value is 0. If you move away from the origin, then R value will increase. And as you go up to infinity, you can identify any point here. So by rotating 5 around 2 pi, you can go to any point on the left side, on the back side, on the right side. By rotating theta from 0 to pi here, you can go to any point in this three-dimensional space above the xy plane and below the xy plane. Yeah, that's how it is. And what about the coordinate surface? Suppose you fix the value of r, and phi and theta are variable. If phi and theta are variable, and fix the value of r, the distance from the origin. So if you fix the value of r, the distance from the origin, this is the origin, fix the value of r value is fixed, certain radius, and now if you vary your phi here, if you drop a perpendicular, you vary your phi here, you are moving around the circle. You are rotating your phi from 0 to 2 pi. You are making a circle. If you vary your theta here, once you fix your r, if you vary your theta from 0 to pi, so if you move to this, fix the value of r means this value is also, distance from this origin is also c1 here. So if you fix the value of r, if you vary your theta from 0 to 2 pi, it will make a 0 to pi, it will make a something like this, arc like this. So if you vary your theta here for all this arc, what you're going to get is a sphere. So I hope you can see that. So once you fix the value of r and vary phi from 0 to 2 pi and theta from 0 to pi, you will get a circle of fixed radius, sorry, a sphere of fixed radius, sphere of fixed radius, sphere of fixed radius r equal to c1, or a sphere of radius r equal to c1. So this surface r equal to c1 coordinate surface is now curved surface, curve or sphere. Okay, curve, it is, which is a sphere. And you can fix your phi coordinate variable, phi equal to c2. You can vary r between 0 to infinity, theta between 0 to pi. Now if you do that, fix the value of phi. So let's say this phi is certain angle, phi is fixed. If phi is fixed, you vary r between 0 to infinity, means r can go from 0 to infinity. It can go up to infinity like this. And you can vary your theta from 0 to pi, means you are rotating from this to this. That means r is going to infinity. You are varying theta between 0 to pi here. So you will get some kind of infinite plane like this. It will be an infinite plane. Okay. This will be an infinite plane. Infinite plane. This will extend up to infinity. It will extend up to infinity. It will extend up to infinity downwards also. Because you are varying r between 0 to infinity. Distance you measure from the origin, you vary between 0 to infinity. So it's an infinite plane touching the surface, touching z-axis on one side of the plane. Now, if you consider another coordinate surface, theta equal to c3. Now, just imagine you fix this something like this. Just imagine you fix your theta here. Theta value is fixed. You vary r between 0 to infinity. It can extend up to infinity. Now you vary phi between 0 to 2 pi. Rotate around this in 2 pi. So this can go around this, and then if you rotate around this is a 2 pi rotation along the phi variable, right? Phi goes around in 2 pi. Then you will find that this r can go up to infinity. R can go up to infinity, This is your r, distance from the origin, can go up to infinity. So you will find that this cone, this will be cone having cone having vertex at the origin. At the origin, cone having vertex at the origin. Actually, it's an infinite cone. It extends up to infinity, right? Infinite cone. Now, phi equal to C3. Now, this is also, as you see, infinite cone having vertex at the origin. This infinite cone, as you see, it's a curved surface again, right? Infinite cone is also a curved surface again. So in this spherical coordinate system, you have two curved surfaces corresponding to r equal to C1 and theta equal to C3. So therefore, this can be categorized as a curvilinear coordinate system. Now, what are transformation relations? Almost finished. Yeah, this is how you can represent. If you look at this carefully here, this is the point. This point can be identified using rho r, phi and theta. Whichever you write first, it doesn't matter. Okay, but phi is the coordinate variable which varies from between 0 to pi. Theta is a coordinate variable which varies between 0 to pi. So if you look at this from this point, if you this is the origin r. So if you measure this distance will be the one I made it as a red line. What will be this distance? This distance from the z-axis will be r sine theta. You know that, right? So this itself is also r sine theta. Now this is phi. What will be your x? X will be this quantity hypotenuse, and this is 90 degree. Remember that this is your hypotenuse. If you follow your trigonometry, x will be expressed as r sine phi cos phi. This angle is phi, that means r sine phi cos phi. And your y here will be r sine phi r sine theta sine phi. This is your z coordinate. Z coordinate here will be r cos theta. So these are the transformation relations. Here you can, sorry, this is x. Here you see that x is expressed in terms of r, phi, and theta. And similarly, y is expressed in terms of r, phi, and theta coordinates. And z is expressed in terms of r, phi, and theta coordinates. All right. And I think it should not be a problem to obtain this reverse transformation relations for any one of you. You will just perform the square of x, square of y, square of z, and then add all these things. And you know that trigonometric property sine square theta plus cos square theta equal to 1, or sine square phi cos square phi, it is still equal to 1. So if you follow that, you will simply get this reverse transformation relation. Here you see that r can be expressed as a function of x, y, and z. And similarly, your phi, you will get the transformation relation like this. And where is that? Yeah, your theta also, this is the theta. Here you see that theta can be written as, sorry, theta can be written as a function of x, y, and z. So if you follow all these steps, you can get the reverse transformation relation, which we normally express it like this. Okay, now what is the position vector? Position vector, you know that this is x I cap plus y j cap plus z k cap. So you simply put x as arc sine theta cos phi, y as this, and z as this. This is your position vector. Once you have the position vector, then you can obtain your scale factors. So the first scale factors, h1 is your hr now, because u1 is r now, u2 is phi, u3 is theta. Okay, here I use it the other way around, sorry. Let's follow this notation. u2 is theta, u3 is phi. So if you do that, the scale factor h1 is hr will be del r upon del differentiation of the position vector with respect to the r coordinate variable, take the magnitude of that. This is what you're going to get. So by taking the magnitude, this is what you will get. And if you combine these two terms, sine square is common factor here, therefore cos square plus sine square is 1, and the remaining will be this, and you will find that your hr is 1. And your h phi h phi is you just differentiate this position vector with respect to phi here. Sorry, position vector with respect to theta here. H2 is your h theta. So del r upon del theta. This is differentiation of sine is cosine. Differentiation of sine is cosine. Oops. How is that? Yeah. Differentiation of sine is cosine. If you follow that, differentiation of cos theta is minus sine theta. This is simple differentiation. So if you do this algebra, when you take the magnitude, r square will be common factor. You take it out of the square root, it is r. And if you simplify this thing using trigonometry again, this will be r. And similarly, the h phi scale factor, you can obtain it. H phi scale factor is differentiating the position vector with respect to phi. This is what you will get. So h phi is r sine theta, h theta is r, hr is 1. What are the unit vectors? Unit vectors are er cap. Er cap is this upon magnitude. So you just simply put this del r upon del r, and you put your hr value. This is what you're going to get. Unit vector along the r coordinate variable. Unit vector along your theta coordinate variable will be this. Unit vector along your phi coordinate variable will be this. So that's exactly the same thing that you have to follow. Tangential unit vectors. And you can prove that this spherical coordinate system is orthogonal system by taking a dot product between these unit vectors. So you take the dot product between the unit vectors, you will get it. So you can see my notes also. These are something which are given in detail there in the notes also. So just take a dot product, you will get the unit vectors. So these are some simple things. I think with this we can complete our curvilinear coordinate system. The only topic that is left with us is tensor analysis. So tensor analysis, I will do it after your CAT 1. So study those things, and I will give you assignment also. But this week I'm a little bit engaged. So, but hopefully I can give you assignment, and which you have to submit it. With your assignment, you please go to my class notes, work out every steps there, and I hope you will understand the curvilinear system and the vector topics that we have discussed so far. Okay, so I think with this I will end my lecture. If you go through my notes, if you have any queries, you can just text me in WhatsApp, and I can respond to it whenever I have free time. So please do that. All right. Once you type your attendance, you can exit the meeting. I hope you have typed your attendance and exit the meeting by now. All right. I think I will close my lecture now. I hope everyone has typed your attendance.